Currently we're in the square module where we handle the collisions with the block, the walls, and the paddle. The square is the ball that's instantiated inside every single level. Right here we're talking about, at the positive edge of the clock, we are handling the collisions. This here is the collision with the bottom, where once it hits the bottom, we trigger the endgame flag. Down here, we're handling the collision with the blocks. We index with a for loop to check which block has been hit, and depending on which block has been hit and which direction it's been hit from, we change the Y or X direction accordingly. The block module we came up with from scratch, it instantiates at in every single level, and it's the same size every single time. Once it's been hit, it sends a signal to the square module to tell that it's been hit and which direction it's been hit from, so that the square can bounce off in the right direction. This here is our keyboard module, where we take in inputs from the keyboard. We have these case statements to check which button has been pressed, and then reset once the button has been released. Buttons 1 through 8 give you the level select, and the A and D allow you to move left and right.
Talking to you about our game module for our breakout game. So in our game module is where we instantiate the level. So we have 8 different game modules for all 8 different levels. This is because they all work with the same block and square modules and paddle modules. So this is done to keep the code general and reusable. The main outputs of this module are the VGA outputs and endgame score and win to help us switch between states in the finite state machine. And our main input is the user inputs with the button left, right, and our clock. As I said earlier, we have a lot of parameters that set where the paddle is, where the blocks are, and the starting locations of the ball and its starting speed and size. We use all these local parameters to, as I mentioned earlier, be able to use the same block module and the same square module. Everything in this module is done at the positive edge of the clock, and this is where we instantiate all the modules that we will be using and where they communicate with each other in the game, mainly the block, paddle, and ball. This is also where we draw things on screen and where we send it to the VGA. At the bottom here, this is where we draw the edges of the objects and where we set their color to be white.
The level screen, the menu screen, and the game over screen, we are essentially calling a module that does the same thing 3 times. And what that module does, that it just gets a memory file and also gets a memory file for the palette. These are essentially just taking an image and converting it to addresses, and what's ending up happening is that it makes a bitmap. This bitmap is telling the screen which colors should be displayed at each pixel. And in our case, we're mainly doing black and white. However, as you will see in the demo, the level screen has multiple colors. And the code is not, for the memory files are not here, but the idea is that these memory files, for example, levels.mem, is being read by the SRAM module. Levels.mem has it's basically full of a list of addresses. So for example, if line 1 is, say, freef, right? If it's freef and the corresponding palette to freef is 00f, every time it sees freef in levels.mem, it means that it's going to put out the color 00f. So that's the general idea. This is being done for our game over screen, our level select screen, and our menu. Something that is important to note is that these memory files were very hard to generate, just mainly because we went off of the previous code. They used a Python script, image2fmem, and what this script, last time it was updated was around 2020, and what ends up happening is that it takes only very specific inputs. That being said, our main idea, our hope was that we could use multiple of these to make some sort of like a better animation in the menu screen and in the game over screen. But we kind of gave that idea up because we realized that we are using quite a bit of block RAM, and reading two memory files that are not the palette ones in the same module was proving to be very difficult because it was just hard for the FPGA to do.
And I'll be explaining the FSMs for the 7-segment display and the game state as well as the top module. So here we have the level select FSM. So it outputs the current state, which is used in the top module, and as inputs it takes in the win flag and the lose flag along with the spacebar, which is other in. So here we cycle through this. Here is where the states are declared. So start menu only goes to level select once you press the spacebar, and level select obviously goes into the levels when you press the corresponding number on the keyboard. And then game over goes back to level select after you press the spacebar. And then down here we have what happens when you pass the win flag in each level. It just goes to either level select if you win or game over if you lose. And then for our 7-segment display FSM, in here we take in both the high score and the current score, which goes through this small score track module that keeps track of the score. And then so we have the states cycling through the anodes, and then we have a binary to BCD converter that we borrowed off the internet. And then down here we make sure that the correct BCD value is being shown to is being put on the correct anode. And then here's our top module where everything is instantiated. So here we have the parameter for the max score that determines our win state for each game. And then the VGA outputs here are determined by the state that the game is currently in, which comes from the level select FSM that I showed earlier. And then we also, in each state, depending on what state it is, we reset any values that have to be reset, such as the lose flag and the win game flag, along with the scores, because we don't want to display those when we're outside of a level.
So this is our menu screen. What this is doing, it reads a memory file, fr.mem, and with the palette, it just generates, it's just black and white. But again, because of the issues of generating the files, you can see it has to, at least at some point, make some weird distinctions with around the black and white to generate an actual image. And then this animation originally was going to be another memory file, but we just decided to just write a black block on top of it on a specific clock, so it just looks animated. And then after that, we just go on the keyboard, we press the spacebar to go to the level select screen, and then once we're in the level select screen, we can go into any level. So for example, now we're in this level, EC311 or level 7. We have 8 levels. There are 4 different level designs, and each even number level is the odd number before it, that level design, but faster. So right now we are on level 7, so it's going to be a bit slow, but that's the idea.
Level 8 has the same design, but the ball moves much faster.
So,
and then here we can also see the score incrementing when we hit a block.
The 7-segment display, the 4 bits on the left are meant to show the highest score of the level, and on the right is going to be displaying the update. So as of yet, we have yet to hit another block. Right now,
hit a block there, and it updates to 30 and then 35 because we hit 2.
Right there.
Every block we hit increments the score by 5.
So we're just gonna demonstrate the game over screen now because this level is a bit slow, but we just wanted to show the sign first. Then we go to the game over screen.
And you can also see that the score resets because we're no longer in the game.
We're here. We go back to the level select by pressing the space bar.
And if we go back to level 7, we can see that the level regenerates.
So it draws all the blocks and it generates all the collisions perfectly fine. So that's the plus. Now if we were to go to say, just to show the different designs we have, if we go to like level 1, we get to see like a pretty standard breakout. And again, the scores being updated different per level. It depends on the number of blocks the level has, which is different. So that's one pattern we have. If we go to level 3, we have this different pattern. And the speeds of the balls per odd level is just going to show us playtesting to see which works best and what is like more playable. If we go to level 5, we have this nice cute heart, same physics. And this level has ended up being pretty satisfying because we get to be inside a loop and that's pretty fun. We wait here for a moment.
A long moment.
This is also a good demonstration of working game physics. Seems to be all in check.
And then if we go to a faster level and we can win more quickly, then we can also demonstrate the winning.
When we win, we're just gonna be sent straight back to level select. So and we're back to level select. So that's essentially the whole thing about our game. So that's just generally all the things we have to show. As I mentioned, the odd number levels are just going to be the new designs, and the even numbers are just the previous odd number, but different, like a faster speed to just make it more challenging. So yeah, that's just a good way of showing all of our code in action.